So today we will begin the formal theory of addition of angular momenta. Okay, so thus far we have sort of laid the groundwork by talking about what it is that we mean by direct product space and direct sum space and things like that. So today we will actually talk about how to formally add to angular momenta, and we'll also in the process see why the mathematics that we had talked about is relevant to the problem. Okay. So before I begin, I need to say a few words about the notations that I will employ. Unfortunately, there will be a slight change in the notations that I will employ, and I will tell you why. So thus far, I have called any angular momentum to be J, right? And I've denoted the components of the angular momentum by Ji, which is J1, J2, J3. Okay. Now, when I add two different angular momenta, I need to add two angular momenta that live in two different Hilbert spaces. And at the outset, I have a problem because typically I want to call them J1 and J2. But thus far, I have reserved the one subscript on J to refer to the component of J. So here, of course, I can get rid of this problem by adding two angular momenta, which I can call J and J prime, or J prime and J double prime, but this will be a very cumbersome notation for me to employ, and I might actually miss writing it properly. So the reason, for this reason, I've thought about using a change in notation. So I'm going to call the two different angular momenta as J1 and J2. So when I write J1 and J2 in this class and the next, I don't mean the components of the angular momentum J, but I actually mean two different angular momenta. And when I say J, I mean the sum of J1 and J2. Okay, I'll clarify what this means as we move along. So now this raises the question of how do I see this J1 is a vector. So this is a vector, this is a vector, and this is a vector. So J1 has three components, 1, 2, and 3, and J2 has three components, 1, 2, and 3. So the question is, how do I write the three components? Now, if I have to use just a notation, that is not an issue because I can denote the ith component of J1 by J1i. Okay. So, for example, I equals 1, 2, and 3 so far. But I would frequently need to also explicitly write down the third component of J1, for example. And I don't want to write this J13 because J13 is a different matrix that we have employed in earlier context, right? J13 is actually J2 with our initial notations. Now I can get rid of this by writing J1 comma 3, which is the third component of J1. But again, this makes for some cumbersome notation. So to make the notation easy, I've decided to, just for the addition of angular momentum part, I've decided to call the third component as a Z component. So when I want to write down the Z component of J1, I will simply write J1Z like this. Okay. And that looks like 2. So like this. Okay. So the notation that I will employ for the addition of angular momentum lectures is when I say J1 and J2, they mean two different angular momentum vectors, right? And when I say J, I mean the sum of these two guys. Okay. Now all of these guys have three components. And if I simply have to refer to a general component, I will call this as Ji, the ith component of J, or J1i, J1i or J2i. But when I specifically want to talk about the third component of J1, J2, or J, I will write Z instead of 3 to avoid confusion with our previously defined J13. So I'll write this as J1Z, J2Z, and JZ. Okay. So this is a small note about the notations because this might be a little confusing if because I'm changing things slightly midway. Is this okay with all of you? Okay, so if there is no concerns about this notation that I will employ, I will go ahead and begin. Okay. So what is it that we want to do? We want to understand how to formally add angular momentum J1 with angular momentum J2, right? Okay. So let's see how this proceeds.
Hello, sir.
Yes.
Sir, is J1 and J2 are J1 and J2 representing the angular momentum for different entities or for the same thing, sir?
So they could be anything. So I'm simply writing. So for example, if I'm talking about a single particle that has both an angular orbital angular momentum and a spin angular momentum, right? So then for that single particle, the net angular momentum would be L plus S, right? The orbital angular momentum plus the spin angular momentum. So L would be my J1 and S would be my J2. Agreed? But I can
Yes, sir.
talk about, for example, a two electron system. And in a two electron system, for example, let us say that neither of the two electrons have any orbital angular momentum. They both have a spin angular momentum. Then I can talk about the net angular momentum for the system. In that case, the net angular momentum for the system would be S1 plus S2, right? So in which case, this would be my J1 and this would be my J2. So whatever the context is, whether you're talking about, the net angular momentum of a single particle or the angular momentum of a system of particles, the J is the composite angular momentum. It is composed of the addition of various different angular momenta. Okay.
Yes, sir.
All right. So let us remind ourselves that J1 and J2 being angular momenta satisfy the usual commutation relations that angular momentum generators do satisfy, right? So we know at the outset that, so we want to clarify what this relation means, J1 plus J2, right? So before we begin, let us collect all the information that we do know about everything here. We do know that, for example, J1I, J1J, the commutation of the generators of the angular momentum J1 is IH bar epsilon IJK J1K. Similarly, the commutator of the components of J2 satisfy the angular momentum algebra, right? IH bar J2K. Now, in general, J1 and J2 live in two different Hilbert spaces and have nothing to do with each other. So, which means the components of J1 and the components of J2 commute. Okay. So, the components of J1 and the components of J2 commute. Okay. It is only the components of the particular angular momentum that we are talking about that do not commute. Components of two different angular momenta obviously commute because they have nothing to do with each other. Okay. So when I form the tensor product space of these two guys, I need to understand how is it that a rotation acts, right? So what is, for example, an infinitesimal rotation? Right? What is an infinitesimal rotation? It is basically the direct product of the matrices of the infinitesimal rotations acting on the one space and the two space. So this infinitesimal rotation U of, let us say that acting on some direction n cap delta theta would be 1 plus or minus I j dot n delta theta divided by h bar, right? And this would be equal to 1 minus I j1 dot n delta theta over h bar, direct product 1 minus I j2 dot n delta theta over h bar. And since delta theta is a very small parameter, I can write this tensor product on the right hand side as the direct product of the two matrices 1 minus 1 or 1 and 1. So remember that the dimensionality of the first one and the dimensionality of the second one is in general can in general be different, right? But that is no issue to us because we know how to write down the direct product of two matrices now. Now this would be minus I over h bar. Now I'll write this in one step. So please see if this makes sense to you. J1 direct product 1 plus 1 direct product J2. I'll take off the arrow symbol. Dot n delta theta. Okay, I'll put in. Okay. Plus order delta theta square, which I will neglect. So this is what you would get. So an infinitesimal rotation in the composite space is composed of the infinitesimal rotation in the 1 space and the 2 space with these two matrices added together. So if you compare the left and right hand sides, you can actually see that the generator of rotation in the composite space can be understood as the generator of rotation in the 1 space, direct product, the identity matrix in the second subspace, plus the direct product of identity in the first subspace, direct product, the generator of angular momentum in the second subspace. So when I say J equals J1 plus J2, the shorthand notation that is frequently employed is J equals J1 plus J2. And people write J equals J1 plus J2 in quantum mechanics. This is what they mean. Of course, it is cumbersome to write this down every time. So which is why people simply write J equals J1 plus J2. And it turns out that all the usual manipulations that you can do, figuring out commutation relations, etc., can be done by simply using this shorthand notation. I'll demonstrate why the shorthand notation is actually useful to you in just 1 minute. But does this make sense? Yeah. So this is what we already expected, right? So for example, in the tutorial problem, we actually calculated these matrices for J1 equals half and J2 equals 1. We will revisit that example again, probably tomorrow. Okay. Shouldn't we have a direct sum? No. Remember that when I write down the tensor product like this, right? So J1 has a different dimensionality, 1 has a different dimensionality, but the matrix J1 times 1 is, see, the dimension of the 1 space is 2J1 plus 1, right? And the dimension of the 2 space is 2J2 plus 1, right? But the dimension of the direct product space is 2J1 plus 1 times 2J2 plus 1, right? So for example, when we added the angular J equals 1 and J equals half, the J equals 1 space had dimensionality 3, right? Because the 3 vectors were 1, 1, 1, 0, and 1 minus 1. And J equals half, the dimensionality was 2 because we had 2 vectors, 1 half, 1 half, and 1 half minus 1 half, right? So the dimensionality of the direct product space, so I have this open here, right? The dimensionality of the direct product space was 6 by 6, which is 3 times 2. But when I add these two matrices, just like you added in the tutorial problem, when you, for example, calculate what J3 is in the direct product space, you take the direct product of S3 and I and L3, and you simply add the two matrices. So the J3 itself is just a regular addition of these two direct products. Okay, there is no direct sum here. Okay, because this is a 6 by 6 matrix, the S3 cross I is a 6 by 6 matrix, the I cross L3 is a 6 by 6 matrix, and we are simply adding two 6 by 6 matrices. Okay, that is all. So this is what I mean by addition of two angular momentum. I simply take the direct product of the first angular momentum with the identity matrix of the second subspace, and regular addition of that to the direct product of the identity in the first subspace with the J2 angular momentum of the second subspace. Okay. Now, as I just told you, this is a cumbersome notation, but let us employ this notation to calculate one commutation relation, and then you will quickly discover why this is a terrible idea. So First, we have to first establish that J itself is an angular momentum. Now, this might seem like a silly thing to you because J1 is an angular momentum, J2 is an angular momentum, so J has to be an angular momentum. Fair enough, but we still have to establish that it is. First of all, we are not even sure what would we get if you add J1 and J2 in this particular fashion, right? See, let us say if J1 is 1 and J2 is half, then what is J? Right? We are not even sure what the value is at this point, right? Should it be just 3/2 or should it be something else? So it turns out the answer is slightly more complicated than that. So let us not assume anything about J, and from first principles demonstrate that J itself is an angular momentum by explicitly showing that the components of J satisfy the same algebra as the components of J1 and J2. In other words, if J1 and J2 satisfy these two commutation relations, we have to show that J also satisfies the same commutation relation. And I will show this in the roundabout way by employing this direct product notation. So let us calculate the commutation of J1I, sorry, excuse me, Ji and Jj. Okay. Now, what is this equal to? This is equal to J. When I say Ji, I mean J1I direct product 1 plus J2 1 direct product J2I commutator J1J direct product 1 plus 1 direct product J2J. This is what I mean. Okay. Now we know the commutators of J1I and J2I, and we also know that J1I and J2I commute. So the only terms that could possibly survive in this commutator are non-zero in this commutator are the commutator of J1I direct product 1 with 1 direct product J2J oh, sorry, I made a mistake here, right? This has to be again. Yeah, this is correct. One direct product J2J. Yeah. And the second non-vanishing term should be 1 direct product J2I, comma, J1J, comma, cross 1. Does this make sense? So please stare at this and let me know if you have any questions. So there are terms. Oh, no, I wrote this entire thing wrong. So you should have asked me questions. I'll write this again. See, we know that J1I and J2J commute, right? So we don't have to take any terms with one J1 and one J2. We know that J1I and J2I do not commute. So the only non-vanishing terms are, this is equal to J1I, comma, direct product 1, comma, J1J direct product 1 plus 1 direct product J2I, comma, 1 direct product J2J. Right? This is the correct way. Because terms like, for example, terms like J1I direct product 1, comma, 1 direct product J2J, this is all 0 because J1I and J2J commute. Okay, of course. Yeah, so my Bluetooth is acting up, but hopefully this is showing. Now, this is an important step, so I'll pause here and please ask me if you have any questions. Is this okay? I mean, you can type it in the chat window also, okay? All right, so to evaluate this commutator, we note that I can write this, the first term, since this is a direct product of a matrix A times 1 plus matrix, comma, matrix B times 1, I can as well write this first commutator as J1I, comma, J1J direct product 1, and I can write the second commutator as 1 direct product J2I, J2J. Okay. And I already know that this guy is IH bar epsilon IJK J1K, and this guy is IH bar epsilon IJK J2K. So I can write this entire commutation as IH bar epsilon IJK times the quantity J1K direct product 1 plus 1 direct product J2K. Okay, but this is precisely the kth component of J. Okay, by our definition of what addition of two different angular momenta is, right? So I can write this commutation finally, all said and done. I can write J1I, I can write Ji, Jj as IH bar epsilon IJK JK. In other words, the components of J satisfy the exact same angular momentum commutation relations as the individual components J1 and J2. Okay, does this point make sense? So now you actually realize that it's actually, I mean, while I had actually done this out, remember that I also made quite a few missteps. It is actually quite cumbersome to carry through this notation. So if I had simply used the shorthand notation and simply written J as J1 plus J2, right? Then I can simply write Ji as J1I plus J2I. And if I had evaluated the commutator this way, then I would have written this is equal to J1I plus J2I, comma, J1J plus J2J. And I would have quickly realized that J1 and J1I and J2J commute, and J2I and J1J commute because they are in different Hilbert spaces. So the only non-vanishing commutators here are J1I, comma, J1J plus J2I, J2J, right? And you can quickly show that this is equal to IH bar epsilon IJK JK. Okay. So you don't lose much by employing this shorthand notation, even though the correct way to understand this sum is by this top line in the second page, right? So you should understand the addition as the direct product of the two different matrices and then take the regular sum of those two different matrices. But to manipulate commutation relations and so on and so forth, it is much easier in many cases just to employ the shorthand notation. So the J, the composite J, whatever this composite J is, we do not know what the eigenvalues of this J is at this point. We are not yet ready to answer that question. But whatever this J is, it certainly qualifies to be an angular moment. Okay, so that much we have established. Okay. So let us slowly try to understand the different parts of this composite space. So what is it that we mean when we say that we are taking the tensor product of two different spaces? Well, let us actually remind ourselves that the individual Hilbert spaces for J1 and J2 is constructed out of the simultaneous eigenvectors of J1 square and J1z and J2 square and J2z. So in the space 1, right, you have J1 square acting on J1 M1 equals H bar square times J1 plus 1 acting on J1 M1, and J1Z J1 M1 is M1 H bar J1 M1. Okay. Similarly, in space 2, you have J2 square acting on J2 M2 equals H bar square J2 plus 1 J2 M2, and J2Z acting on J2 M2 will simply give me M2H bar J2 M2, right? Now, what do I mean by the direct product space? The direct product space is usually composed of the basis vectors, which are a direct sum of these two basis vectors, right? So the direct product space, the basis vectors are J1 M1 direct product J2 M2. Okay. Now we don't need new notation for these basis vectors. So I'm going to call them J1 J2 semicolon M1 M2. Okay. So to be very specific, what I mean this. So when you look at so if you look at this problem, right? So when we worked out the addition of 1 and half, we wrote down these eigenvectors, right? These eigenvectors are the direct product of the vectors in the first space with the vector basis vectors in the second space. So these are the eigenvectors that we are talking about, right? So these are the eigenvectors which I'm calling as J1, J2, M1, M2, which is a direct product of J1, M1 and J2, M2. So let us be actually more specific about what these basis state means, right? These are the basis states in which I can be assured that a measurement of J1 will give me h bar square J1 times J1 plus 1, and a measurement of J2 would give me h bar square J2 times J2 plus 1. Measurement of J1Z will give me M1H bar, and the measurement of J2Z will give me M2H bar. In other words, these basis states J1, J2, M1, M2, J1, J2, M1, M2 are the simultaneous eigenkets of the four, commuting operators J1 square, J2 square, J1Z and J2Z. Right? In fact, this is how you actually construct Hilbert spaces in general, right? So you look at all possible operators that commute, and you take the space as the simultaneous eigenvectors of the maximal commuting set of operators. In this case, this turns out to be 4. This is the explicit construction that we have done thus far.
Sir,
Yes.
sir, yes, sir. These direct products are defined for these operators, or more specifically for matrices. So how we are calculating the direct product for these states like G1 M1 direct product with J2 M2?
Okay. So remember. So did you work through the last tutorial sheet?
Yes, sir. Yeah.
Okay. So let me use the same example so it refreshes your memory. Right. So we added, for example, a spin half with a j equals 1. Right. Now the basis states, is this okay? So J1, yes, M1 for these guys were 1, 0 and 0, 1. Right. And yes, J2, M2 for these guys were 1, 0, 0, 0, 1, 0 and 0, 0, 1. Agreed?
Yes, yes.
Now we wrote down the basis states in the tensor product space, and we defined the tensor product space as being composed of the direct product of the eigenvectors of the j equals half and the eigenvectors of j equal to 1. So for example, I think we call this E1, E2 and these as F1, F2, F3, right? Okay, but we can call it whatever we want, right? So now I'm calling it J1, M1 and J2, M2, right? We are just labeling it by the M2 index. But whatever it is, so let us look at a particular example. So J1, when I say J1, M1, direct product J2, M2, I mean the 6 basis vectors that are gotten by the direct product of these two guys. So let me take, for example, this and direct product of this with this, right? So what do I mean? So 1, 0 with 1, 0, 0, right? So what is this? This is equal to, this is a 6 dimensional column vector. So I take the first entry here and I multiply this first entry with first this guy and this guy and this guy. And that will be the first 3 entries of this column matrix. So 1 times 1 is 1, 1 times 0 is 0, 1 times 0 is 0. Okay. Now I take the second entry here and multiply the second entry with 1, 2 and 3. Okay, pairwise. So I'll get, since this is 0, I'll get 0, 0, 0. Okay. Is this okay?
Yeah, sir. Now
Our
it's more
present
clear.
notation, this would be the eigenket 1/2, 1/2. This would be the eigenket 1, 1. Okay. So what we have just found out is that the direct product 1/2, 1/2 with 1, 1 is giving me the 6-dimensional column vector 1, 2, 3, 4, 5, which I'm calling in my new notation as J1, J2, 1/2, 1, M1, M2, 1, 1/2. Okay. This is the notation I'm employing. Similarly, I can calculate the direct product of, for example, 1/2 minus 1/2 with 1, 0. Okay, what would this be? So 1/2 minus 1/2 is, let me use a different color. 1/2 minus 1/2 would be this guy, yeah? And 1, 0 would be this guy. So if I take the direct product of these two matrices, these two eigenvectors, what would I get? I should first take the first element of the first guy, which is 0, and multiply it by all three. So I'll get 0, 0, 0. Then I'll take the second element of the first guy, which is 1, and multiply it with all three of the second guy, which will get 0, 1, 0. Okay. So this is what we have called J1, J2 in this case is 1/2, 1. And M1, M2 in this case is minus 1/2 and 0. Make sense?
Yeah, sir. Clear, sir.
In terms of that example, this is exactly what I'm doing. I'm simply changing the notations. Now, many books also, for brevity, suppress the J1, J2 here, right? And instead of calling this J1, J2, M1, M2, some of them simply just label this by the M1, M2 index also, right? But I'm not doing this. I'm simply using all four just to make sure that you understand that these are the eigenkets of the 4 commuting operators: J1 square, J2 square, J1 square whose eigenvalue is J1, J2 square whose eigenvalue is J2, J1z whose eigenvalue is M1, and J2z whose eigenvalue is M2. Okay. Okay. Now to answer the second question. What is the confusion? So Niyati, you said I don't understand. So which is the part you don't understand?
Sir, I didn't get how these are called. These are the simultaneous eigenkets of all these operators. Can you please?
Okay. See, so it is one thing to simply say that these are the simultaneous eigenkets. We also have to prove, right, that these are the simultaneous eigenkets. In other words, let us actually show it using this example itself, right? So let us take, for example, so what do I mean by this, practically speaking, right? So when I say that this is the simultaneous eigenkets of J1 square, J2 square, J1z and J2z, remember that in this case, for example, remember that for J1 equals 1/2 and J2 equals 1, all matrices are 6 by 6, right? So all I mean by this statement is the following. So if I construct the 6 by 6 matrix J1 square, how do I construct the 6 by 6 matrix J1 square? Well, I will construct the matrix so I'll construct the matrix J1 times 1, right? This will be a 6 by 6 matrix, right? So when I say J1 square, I actually mean that I'm talking about this matrix, right? So this is a 6 by 6 matrix. Similarly, when I say J2 square, I mean, excuse me, this 6 by 6 matrix, right? And when I say J1Z, I mean the exact same thing again. So J1 Z direct product 1. Okay. So let us take, and similarly J2Z is 1 direct product J2Z. So these are all 6 by 6 matrices. So when I say that these eigenkets, for example, like 1 with 5 zeros and 4 zeros, 1 0, and all these eigenkets are the eigenkets of this with definite eigenvalues, I mean that if you take these four matrices, okay, and act it on these eigenkets, you will get the corresponding eigenvalue times the eigenket back again. So let us actually show that this is true by looking at, I think I closed it, but let me open the tutorial, just 1 minute. Okay, so this is your tutorial, right? So we actually worked this out. So let us actually look at, for example, J3. Okay. So if, okay, so we did not work out the J1 square and J2 square matrices, but suppose if you acted, for example, this J1Z direct product 1. So let us actually do this. So let us compute J1Z direct product 1. What is J1Z? This is, I'm adding half and 1. So this will be h bar over 2, 1, 0, 0, minus 1. Direct product 1, 0, 0, 0, 1, 0, 0, 0, 1, right? I think we calculated this part, if I'm right. We call this S3 cross I, right? Okay. I actually made a mistake. This has to be h bar by 2 here, anyway. So this would be h bar over 2. Again, you know how to calculate this. I'll take the first element and multiply it with the every element of the second matrix. So I'll get 1, 0, 0, 0, 1, 0, 0, 0, 1. The second guy is just 0. The third block is simply 0. And the fourth block is minus 1 times an identity matrix. So it will give me minus identity matrix. Okay, so do you agree that this is J1Z direct product 1? Yes or no?
Yes, sir.
Okay. Now let me act it on one of the eigenvectors. So let me take, for example, this eigenvector that we have written here. What is this? This is the direct product of 1/2 minus 1/2 and 1, 0. Now what is it that I have written here? I have simply written J1Z direct product 1. So this is the 6 by 6 matrix representing J1Z. So this is only going to measure the Z component of the first angular momentum. It has nothing to do with the second angular momentum because the second guy is just identity. Okay. So now let me ask, how does this 6 by 6 matrix act on, for example, the direct product of 1/2 minus 1/2 and 1, 0? If I act J1Z direct product 1 on this eigenstate, I should simply pick out the Z component of the first angular momentum. Do you agree? Yes or no? So all I'm saying is that J1Z direct product 1, for example, in this case, acting on 1/2 minus 1/2 direct product 1, 0. Right? How should this act? The operator itself measures the Z component of the first angular momentum. Right? So the J1Z has nothing to do with the 1, 0 ket, right? Because the 1, 0 ket comes from the J2 equals 1 space. So it's only going to pick out the JZ value of the first guy, which is minus 1/2 minus 1/2. So let us actually check that this is actually true. So take the 6 by 6 matrix, h bar over 2, 1, 0, 0. Okay, and act it on this particular direct product of these two basis kits. The direct product of these two basis kits is this guy, right? This is 1 in the fifth entry and 0 everywhere else. So I'll get 0, 0, 0, 0, 1, 0. What is this equal to? This is equal to, see, everything is 0, but the fifth row will have minus 1. So I can write this as minus h bar over 2, 0, 0, 0, 0, 1, 0. Okay. So which means that this direct product basis is an eigenkit of J1Z with the eigenvalue corresponding to the eigenvalue of the J1 that this kit was constructed from. Does this make sense? Similarly, if I calculate one direct product J2Z on the state, I will get the J2 of the second guy, which in this case happens to be 0. If you want a more non-trivial example, if I calculate one direct product J2Z on 1/2 direct product 1 minus 1, I will get minus h bar times the same state back again. Similarly, if I calculate J1 square direct product 1 on this composite space, 1/2 direct product 1 1 or whatever it is, what will I get? I will get the eigen value of J1 square. So this will be h bar square times square root of, sorry, h bar square times J1 plus 1, which is 1/2 times 1/2 plus 1 times the same state. And this you can verify, you don't have to trust me. Just take this particular example and go through every one of these operators one by one. First construct all these 6x6 operators and add them on these basis kits one by one. And you can actually show that J1 square, J2 square, J1Z and J2Z are actually commuting observables, and that these basis kits that we have just constructed are simultaneous eigenkits of all 4 of these operators. Okay? Does that make sense?
Okay, sir.
No, okay is not good. So does anyone have any questions?
I got it, sir.
You got it. Anybody else?
Sir,
Yes.
sir, can you go to the first slide when you started up with the rotation operator? Yes, sir. Here. Sir, like here we are constructing the the infinitesimal rotation operator for the space in for the space in for J1 and J2. Okay, so like we have this operator which conserves this mapping bit for J1 and again conserves this mapping for J2. So why isn't it like this rotation operator of J1 direct product with I into I direct product with rotation operator of this J2?
Sorry, what?
So like when we write this when I write this operators for the direct product space, I write a direct product B is equal to a direct product with identity into simple multiplication, identity into direct product of B. Here I'm constructing a rotation operator for again a direct product space of J1 and J2.
Correct.
So why isn't the rotation operator of the form to preserve the mapping for both those spaces isn't in the form of
it is. See, that is exact. So when I write the infinitesimal rotation as a direct product of the infinitesimal rotation of the first guy with the second guy, that is exactly, oh, sorry, this is not showing up. So give me 1 second. So when I write this as a direct product of this infinitesimal rotation and that infinitesimal rotation, that is exactly what I mean. Okay. So the question is, how do the generators add? See, if I claim that the generator J1 rotates the kets in the first space by an angle delta theta in the n direction, and the generator J2 rotates the kets in the second space along the same direction n by some other angle delta theta, then what is the generator in the product space that rotates the product basis, like the tensor product of the two basis kets, by an angle delta theta along the direction n cap? That is the question I'm asking, right? The composition itself can be understood as the direct product of the first infinitesimal rotation times the direct product of the second infinitesimal rotation. Now, when I expand this further, I find that the generators have to add according to this particular rule, that the composite generator J that rotates the basis kits in the tensor product space by an angle delta theta along the direction n is equal to the sum of the matrix J1 direct product 1 and 1 direct product J2. But your statement that it has to be A cross B is basically what I do in the first step when I calculate the direct product of these two matrices. In fact, I can extend this to the finite rotations also, because finite rotations, I simply have to take the large n limit of these two infinitesimal rotations. So I can also claim, I'll write it in the, I don't have space here, so I'll write it here. So I can also write that e to the minus I j dot theta can be understood as e to the minus I j1 maybe over h bar j1 dot theta direct product e to the minus I j2 dot theta over h bar. That makes it explicit, right? So what I did there was to take the infinitesimal limit of this particular equation.
Okay, so in the J1 and J2, the expression that we have got, that is the form of A cross I and I cross B, right? In the
A cross I and I cross
a direct product with I and I direct product with B. The form of J, the form of J that we have got.
Yes, the form of J that we have is basically J1 times 1 plus 1 times J2. Yeah, exactly.
Yeah.
So this was a way of showing how it comes about, that is all. Okay, any other questions? Okay, so I'll erase, since this is important, I'll erase these guys. Anyway, I'll let these be because people can refer back to these things. Okay. All right. So let us actually collect whatever I said in words in the form of 4 equations. So we have constructed the tensor product space by calculating the tensor product or direct product of the basis kits for the 1 space and the 2 space. And we have called these kits as J1, J2, M1, M2. Okay. And this is these are the simultaneous eigenkits of the 4 commuting observables, J1 square, J2 square. Did I already write this down? No, I did not. So I'll write this explicitly. J1Z and J2Z. So we'll write this down like this. So all I mean is J1 square acting on J1, J2, M1, M2 is M2, and J1Z acting on J1, J2, M1, M2 is M1H bar. Similarly, J2 square acting on J1, J2, M1, M2. This is 2. So J2, J2 plus 1, J1, J2, M1, M2, and J2Z acting on J1, J2, M1, M2 is M2H bar times these. Okay. Anyway, this is what we just discussed, but I have written this down in terms of equations also. So these product states that we have written down, which is the direct product of the J1 M1 basis kits with the J2 M2 basis kits, in the product space with 2j1 plus 1 times 2j2 plus 2, 2j2 plus 1 dimensional matrices are still the eigenkets of the 4 operators j1 square, j2 square, j1z and j2z. Okay. Now we will ask a different question. Well, we went into the trouble of constructing J, right? And we want to understand what are the eigenvalues of J. So we constructed J as, for example, J1 times 1 plus 1 times J2. And for example, we also constructed Jz, which is J1z direct product 1 plus 1 direct product J2z. And we also established that these J's satisfy the angular momentum commutation relations. So I can actually show that J square Jz equals 0, while Ji Jj satisfies the angular momentum commutation relations, right? So this we showed explicitly, and this, the first one, you can also easily show. So now I can ask myself the question, well, in this composite space, why don't I measure J square and Jz instead of simply worrying about the J1 and J2 and J1z and J2z? For example, wouldn't it be more useful for me to ask the question, what are the eigenvalues of the J square operator? What are the eigenvalues of the Jz operator? So the easiest thing would be if these eigenkets were also eigenkets of, for example, the J square operator. Right? Then I don't have to do anything else. I can simply take the J square matrix and act it on these eigenkets and figure out what the J square eigenvalue is. Remember that just because I know the J1 and J2, I don't necessarily know the eigenvalues of the J square operator. So let us actually be careful about what the J square operator is. What is this J square that I'm talking about? Well, J square is J1 plus J2 whole square, right? So this is equal to J1 square plus J2 square. Now, this is you might think that I had to write this as J1 dot J2 plus J2 dot J1, but I don't have to bother because J1 and J2 are two different matrices in two different Hilbert spaces that commute. So I can always write this as 2 times J1 dot J2. Okay, nothing lost. Now, there's a couple of ways in which I can think about this. Look at this J square matrix. Well, J1 square is a scalar operator and J2 square is a scalar operator, right? It's a square of a vector, it's a scalar. Now we might be tempted to think that J square commutes with J1 square and J square commutes with J2 square. And this is actually true. J square does commute with J1 square and J square does commute with J2 square. But what about the last term? Does J square commute with J1 dot J2? Can anyone think about this? Okay, so I will leave it as a tutorial problem. Let me ask a different question to you guys then. So you can establish that J square commutes with J1 square, okay? You can also establish that J square commutes with J2 square. But what are these eigenkets that we're talking about? These are the simultaneous eigenkets of J1 square, J2 square, J1z and J2z. Does J square commute with J1z? Does J square commute with J2z? See, the question that we're asking is, can I measure J square on these states? So these states in the direct product space are the simultaneous eigenkets of J1 square, J2 square, J1z and J2z. There is two ways in which I can pose the exact same question. Does J square commute with J1z or J2z? If J square commutes with J1z or J2z, then I can, these are also the simultaneous eigenkets of J1 square, J2 square, J1z, J2z and J square. But it turns out that we are not so lucky. J square does not commute with J1z or J2z. So it's not very hard to show this. Let us actually show this. J square commutator J1z. What is this equal to? This is equal to the commutator of J1 square with J1z plus the commutator of J2 square with J1z plus the commutator of 2 J1 dot J2 with J1Z. Agreed? Now, J1 square commutes with J1Z, right? So the first term is 0. Now, J2 square has nothing to do with J1Z. They are in two different Hilbert spaces. So this commutator is trivially 0. But how about the third one? This is equal to, so let me actually write this down. This is equal to 2, for example, this is basically J1I, J2I. That is what I mean by J1.J2, right? With J1Z. Now, J2I trivially commutes with J1Z. So I can write this commutator as 2, J1I, J1Z, J2I. And this is not 0. Because J1, for example, this is J1X commutator and J1Y commutator. So J1X doesn't commute with J1Z and J1Y doesn't commute with J1Z. So J squared does not commute with J1Z, which means that these 4 eigenkets that we have cannot be the eigenkets of the J square operator also, because J square does not commute with J1Z or J2Z. So similarly, you can also show that J square J2Z is also not equal to 0. So what I'm basically saying is that I cannot measure J square and J1Z simultaneously. I cannot measure J square and J2Z simultaneously. Okay. But I can measure J square and J1 square simultaneously. There is nothing wrong. So J square, J1 square would be again J1 square plus J2 square, J1 square plus 2 J1I, J2I, comma J1 square, right? Now the first is 0. Oops. The first is 0 because J1 square commutes with itself. The second is 0 because J2 and J1 are in different Hilbert spaces. And the third is also 0 because J1 square commutes with any component of J1, right? So this is also 0. So J1 square does commute with J square does commute with J1 square, and J square does commute with J2 square, but J square does not commute with J1Z or J2Z. Okay. So if I want to write down, if I want to measure the eigenvalues of J square, for example, these eigenkets that I have written down are a bad set of eigenkets to use. Does this make sense? Is this point clear? The question that I'm asking is, if I add two angular momenta J1 and J2, what should be the resultant angular momentum? Okay. To measure the resultant angular momentum, first of all, I need to figure out the, write down the matrix for the resultant angular momentum and diagonalize them and write down the eigenkets of this matrix. So what I'm trying to say is that the eigenkets of this matrix cannot be J1, J2, M1, M2 eigenkets that we've written down, because the J square matrix does not commute with J1Z or J2Z. Is this point clear? Even though J square commutes with J1 square and J2 square, it doesn't commute with the other two operators in this maximal set of commuting operators that they've written down. So we need to, if we want to figure out if we want to measure J square, we need to write down the another set of maximally commuting operators, of which J square is a member. We already know 3. So this is, for example, let us call this set A. Set A is one in which the maximal commuting operators are J1 square, J2 square, J1Z, and J2Z. But I can write down set B. Set B would be, for example, the simultaneous eigenkets of J square, J1 square, J2 square. Okay. Now, whenever you are constructing a Hilbert space, you always look for the maximal number of commuting generators. So now you ask yourself the question, this is a maximal set. Is there any other operator that commutes with these 3 matrices? then I can construct the simultaneous eigengets of all 4 of these operators. And the answer is we're actually missing out one. There is one other operator that you can write down that commutes with these 3 operators. And that operator is actually Jz. It turns out that even though J square does not commute with J1z or J2z, it does commute with Jz, which is the sum of J1z and J2z. We will actually show this explicitly. And then after that, I'll pause and ask if there is any questions. So let us actually show this. We just showed that J square J1z is not equal to 0. And we also showed that J square J2z is not equal to 0. And now we are claiming that J square Jz is equal to 0. Okay, so somehow if we add these 2 guys, it does commute. Again, please understand the power of the shorthand notation, right? Otherwise, I'll have to write down direct products everywhere. But I will simply pretend that Jz can be written as J1z plus J2z. Now this plus is okay. This is how you add the 2 matrices. But J1z is actually J1z direct product 1. And J2z is 1 direct product J2z. And I'm suppressing this correct notation. So how do I show that this is true? Well, let's write this down. So J square Jz equals J square J1z plus J square J2z. Okay. Now this is equal to J square can again be written as J1 square plus J2 square plus 2 J1 J2. So this is J1 square J1z plus J2 square J1z plus 2 J1I J2I J1z plus J1 square J2z plus J2 square J2z plus 2 J1I J2I J2z. Okay, as we have already figured out, this is 0, this is 0, this is 0, and this is 0. So the 2 non-trivial commutators for our case are, this is equal to 2 J1I J2I comma J1z plus 2 J1I J1I J2I comma J2z. Okay, so this is equal to 2. Now J2 commutes with J1 because they are 2 different matrices. So I can write this as J1I J1z times J2I. And again, I can write the second guy as J1I J2I J2z. Okay. Any questions about any of these manipulations? Any questions or any comments? So I strongly encourage that you also try all these calculations after the class is done. So this is equal to, now let me write this down explicitly in terms of x and y, right? Because when I write J1.J2 or J1I J2I, I mean that I'm writing down 3 different terms: J1x J2x, J1y J2y, and J1z J2z. Now J1z obviously commute. So the non-trivial commutators are J1x and J1y. So let me write this as J1x J1z times J2x plus J1y J1z J2y plus 2 J1x J2x J2z plus 2 J1y J2y J2z. Okay. Any questions? Is this okay? I need some kind of an input so I know if I should stop or continue. Any questions about these manipulations, or is this clear?
Clear.
Clear? Okay. So what is this? The commutator of x and z is minus y. So this is equal to, the first commutator is So the commutator of z and x is 1. So x and z is minus y. So this is minus 2 j1y j2x. What is the second guy? Again, the commutator of j2x and j2z is minus j2y. So this is minus 2 j1x j2y. What's the third term? The commutator of j1y and j1z is plus j1x. So this is plus 2 j1x j2y. The last term is plus 2 j1y. The commutator of j2y and j2z is plus j2x. Okay, and this is 0. Now you may object saying that j1y j2x cannot cancel. If I have written it as j2x j1y, but since j1 and j2 commute, the order here doesn't matter. So if I had written it down in the opposite order also, they always cancel. So pairwise, these four terms cancel, right? So the j1y j2x here cancels the j1y j2x here, and the j1x j2y here cancels the j1x j2y here. Okay. So j square, even though it doesn't commute with j1z or j2z, it actually commutes with the addition, which is j1z plus j2z. So there is another set of 4 maximally commuting operators that I can write down, and these four operators are set B. One can instead employ the simultaneous eigenkets of j square, jz, j1 square, and j2 square as the basis kets of the direct product space. So there is 2 options we have. The first option is the direct product kits are basically the direct product of the eigenkets of the first guy and the eigenkets of the second guy, which is what we computed exactly. And this turned out to be the simultaneous eigenkets of j1 square, j2 square, j1z, and j2z. But if we want to measure j square, for example, these basis kits are not very useful because they are not the eigenkets of the j square operator. So we can think of 4 other commuting observables, and these 4 other commuting observables are j square, jz, j1 square, and j2 square. And I can instead work with this basis. So as I've repeatedly emphasized, there is nothing sacred about basis vectors, right? I can always go from one basis vector to one set of basis vectors to another set of basis vectors by some unitary transformation. Okay, so I'm claiming that if I want to measure j square and jz instead of j1, j2, j1z, and j2z, I will use a basis transformation and go to a different basis. And this basis I will denote by the eigenvalues of these 4 operators. The eigenvalue of j1 square is j1. The eigenvalue of j2 square I will denote by j2, and the eigenvalue of j square I will denote by j, and the eigenvalue of jz I will denote by m. Okay. So there is 2 possible, and these are not the eigenkets. For example, in this tutorial 3 problem, these basis kits have nothing to do with these. Where is this? These kits, right? So this one with 5 zeros, 0, 1, 0, 0, 0, 0, these are all the first set of basis kits, which is the direct product of the basis vectors of j1 m1 and j2 m2. But these are different sets. We should actually figure out what these sets are, and we will figure out what this set is tomorrow for that particular example. But what I'm basically claiming is that I can employ a different set of basis vectors. Again, some 6 dimensional column vector, for example, in that particular example. This should also be the same dimension as the original space because I'm not changing the dimension of the space. So this is also 2j1 plus 1 times 2j2 plus 2 space. But on this space, I'm claiming that I'm using a different set of basis vectors, and these basis vectors are such that J square acting on J1, J2, Jm gives me h bar square times J into J plus 1 times J1, J2, Jm, J1 and J, excuse me, Jz, J1, J2, Jm measures the Z value of the J operator, and J1 square gives me and J2 square gives me J2 plus 1. Okay. This is my second basis kit. So, of course, I need to understand how these two kits are related. We will understand how these two kits are related. But first, recognize that both these sets are perfectly good basis vectors because they are the simultaneous eigenkits of Hermitian operators. So they are properly orthogonal, and we can normalize them if we want to, and we'll assume that these are already normalized. So they form a complete basis. So what do I mean by that? I mean that, for example, in the first set, set A, my kits are J1, J2, M1, M2, right? So completeness, for example, here means that, remember here J1 and J2 are fixed, right? For each J1 and J2, there is various values of M1 and M2. So my eigenkits are basically enumerated by the eigenvalues M1 and M2. So basically M1 can go from minus J1 to plus J1. M2 can go from minus J2 to plus J2. So J1, J2, M1, M2. J1, J2, M1, M2 equals 1. This is what completeness relation means. We need to figure out what the completeness relation for the second set of kits corresponds to. What is set B? Okay. Now here, my J1 and J2 are again fixed, right? So I'm adding, for example, J1 equals half and J2 equals 15 or whatever it is, right? So what is actually changing here is my possible values of J I can get because of this addition. And for each J, obviously, my M can go from minus J to plus J. So my J goes from some minimum value to some maximum value. I need to figure out what these are. But for each J, my M value goes from minus J to plus J. Okay. This is the set of kits J1, J2, Jm, J1, J2, Jm equals 1. Okay, this is the completeness relation for the second set of basis vectors. The only thing that we do not know here is what is Jmin and Jmax, right? Because we have not yet figured out how to add these two, but we will get there. Any questions about any of this thus far? These, all I'm saying, because based on these two statements, is that these are the simultaneous eigenkits of Hermitian operators. So it is fairly straightforward to see that they must be properly orthonormal. And so these form a complete basis kits in this 2J1 plus 1 times 2J2 plus 2 space. In either of these two cases, the dimensionality of the linear vector space, the product space, doesn't change. The product space is 2J1 plus 1 times 2J2 plus 1 dimensional. Okay. In fact, this dimensionality is the crucial ingredient that will help us understand what Jmin and Jmax are. We will answer this question tomorrow. But are there any questions about any of this thus far?
Sir, sir, what was the problem with the set A commuting set A basis vectors?
There is no problem with either of these, right? See, these are both the simultaneous eigenkits of 4 Hermitian operators. Okay. See, it's basically a linear vector space problem that we are looking at. So let us say that you have a set of 5 matrices A, B, C, D, and E. Okay. Now, let us, all of them are some 3 by 3 matrices, right? Just like in this product space, every single matrix is 2J1 plus 1 times 2J2 plus 1 dimensional matrices, right? Now, let us say that A, B commute, AC commutes, and AE commutes. And let us say, for example, CD commutes, and then DE commutes, whatever, right? Now, you can choose, so now you have to construct a basis vector in which the action, you need to construct the basis vectors of a Hilbert space, of a 3-dimensional Hilbert space. And how do you want to construct it? Well, I can simply take 1, 0, 0, 0, 1, 0, 0, 0, 1. There is nothing wrong with this choice. But in this basis vectors, it might turn out that A, B, C, D, E, all 5 of them will be non-diagonal. Okay, so these probably won't be the eigenkets of any one of these matrices. So the way you construct the eigenkets, that will the basis kets that will help you in making your life easier is by choosing the set of matrices for which the basis kets are really the eigenkets of the maximal number of these matrices. So we have to look at the maximal set of commuting operators, right? Now, obviously, I can choose as the basis kets the simultaneous eigenvectors of A and D. Okay, so if I choose that, then in this space, for example, the A would be a diagonal matrix and D would be a diagonal matrix. Okay, or I can choose in this basis set, for example, C and D. Okay, C would be a diagonal matrix and D would be a diagonal matrix. Okay, but I cannot choose, for example, the simultaneous eigenkets of A, B, and C because I am not given that B and C commute. Okay, but suppose if I am also certain that C and E commute. Okay, oh, sorry, this is not showing. Give me a second. Suppose if I'm also certain that in this space C and D commute, then there is one basis choice that makes my life easier than the other basis choice. And that is the basis choice in which C, D, and E are all diagonal. So I will choose, for example, simultaneous eigenkets of C, D, and E. Now, the question is, suppose if I choose, instead of this, suppose if I choose a simultaneous eigenkets of A and B, is this wrong? No, that is not what I'm saying. I'm not saying it is wrong. It is simply that in this particular example, there is a choice that makes your life easier than the other choice. In fact, I can just choose this. And I can be happy with the fact that all 5 of these matrices are off diagonal or non-diagonal. There is nothing wrong with any of these choices. But there is one choice that makes certain problems easier. Does this make sense?
Okay,
now,
so
if I look
like
at set A and set B, set A is the one in which the operators J1 square, J2 square, J1z and J2z are diagonal, which means if I want to ask, for example, if the question that I'm interested in is, for example, what are the values of J1, J2, J1z and J2z, this would be the ideal set to use. I can use this as my basis set. But suppose if I want to ask the question, what are the eigenvalues of J square and Jz? This would not be an good set of basis kits to use, right? Now, there is nothing wrong with the first set or the second set. It just so happens that in the first set, the J square matrix is not diagonal. That is all. These are both genuinely proper basis kits for the direct product space. There is nothing wrong about either one of them. These are 2 different choices that we have that are related by some unitary transformation.
so we could have even checked with JZ commuting with the other operators.
We could have?
checked about JZ commuting with those J1Z and J2Z. We could have checked about JZ. For JZ, we could have checked if it commutes with this J1Z and J2Z.
No, see, JZ will commute trivially, right? See, JZ commutes with J1 and J2 trivially, right? See, once I measure the eigenvalue of J1 and once I measure the eigenvalue of J2, I have measured the eigenvalue of, once I measure the eigenvalue of J1Z and I measure the eigenvalue of J2Z, it goes without showing that I have measured the eigenvalue of JZ because JZ commutes with J1Z and J2Z, right? But the converse is not true. That is the point I'm trying to make. Just because you have measured J1Z and J2Z doesn't mean that you necessarily measure JZ in this eigenspace, because there is other operators in this eigenspace that don't commute with, for example, J1Z or J2Z, right? That is a non-trivial statement. Does this make sense?
Sir, I didn't get what you said.
Okay, see. So we recognize that J square and JZ commute, right? Now forget the fact that J square is J1 plus J2 whole square. J square and JZ commute, right? Now,
Yes.
This is exactly how we have developed angular momentum theory, right? By calculating the simultaneous eigenkets of J square and JZ, right? Make sense?
Yes.
So why don't I just, since I've guaranteed that J square and JZ commute, which we have shown explicitly here, I can ask what are the simultaneous eigenkets of J square and JZ, right?
Okay.
There is nothing wrong with that question. Now it so happens that I can take two other operators along for the ride, J1 square and J2 square. Instead of asking J square and JZ, I can ask J square, JZ, J1 square and J2 square, because those guys all commute anyway. So let me choose the maximal set instead of just talking about J square and JZ. That is set B.
Yeah.
Okay.
Yes.
All right. So we will stop here and we will continue tomorrow. Okay? Since we are running out of time. Tomorrow we will meet at the usual time.